And we are live. Welcome all to the stream for this awesome workshop as part of the IBC Ideathon. I think it's going to be a particularly exciting one. So for those of you who don't know and didn't join in on the last few streams, I am Ollie. I am the DevRel lead here for the Interchain Foundation. I will hand it over to Serene for a quick intro, who is our DevX designer. So yeah, Serene.
Hello, everyone. My name is Serene, and as Ollie mentioned, I'm the developer experience designer. Super excited to be on here and to be supporting Adi during his workshop.
Yeah, excited for this one. So yeah, so myself and Serene might have a few questions for Adi as we go along, but also feel free to ask questions in the chat, which we are monitoring on YouTube as well, as we go through things. But now I will hand it over to Adi, who can introduce himself and get right into the workshop itself.
Cool. All right. Yeah. Hey, everyone. My name is Adi. I work on product at IBC at the Interchain Foundation. Yeah, and I guess I'll be talking about IBC and just interoperability in general today. Yeah, I'll just share my screen. All right. Cool. People can see my screen, right? All right.
Yeah.
Yeah, so we'll be talking about the basics of IBC today, as well as blockchain interoperability. Yeah, so the goal of today is to sort of go through the fundamentals of interop, and talk about IBC. So like, what is IBC? How does it work? What is its architecture? And we'll also talk about some of the other interoperability protocols in the market and talk about their architecture and see how these different architectures sort of look and like what the trade-offs are. Okay, cool. So we hear the word bridge a lot. Like, what is a bridge? It's just some mechanism to transfer information or data from one place to another. And I'll use the word bridge or just interoperability protocol interchangeably here today. And on a very high level, that you can sort of categorize a bridge in three different layers or three different abstraction layers. So there's a state, a transport, and an application layer. And we'll go into these different layers a little bit more in depth in the coming slides, but essentially the state layer is what's responsible for verifying actual state transitions. So like in block number 1, the state is X. In block number 2, the state is Y. So something happened in between. How did that happen? So that is what the state layer is verifying. And that could be through multiple different means, which we'll touch upon. There's a transport layer on top, which is responsible for physically moving the message from point A to point B. And on top of the transport layer, we have applications. And that's what's responsible for performing the actual business logic of things. So in the case of like token transfers or something, this could be minting, burning tokens, or like executing like some random function call, etc. So coming to IBC, what is it? IBC stands for Inter-Blockchain Communication, and it is a general purpose messaging protocol for the interchain. So a bunch of words there. What do they mean? General purpose just refers to the fact that IBC can be used to send any sort of information. It is not just limited to token transfers. You can send any arbitrary data over IBC as long as it's encoded in bytes. IBC can send your message from chain A to chain B. And like I said, it's the messaging protocol for the interchain, and we refer to the interchain as sort of this network of networks, all the blockchains connected over IBC. And similar to TCP/IP that connects, different mobile devices or computers over the internet, IBC aims to become like the TCP/IP for blockchain. So if you're familiar with the internet stack, you have TCP/IP at the bottom at the transport layer, and which is responsible for physically moving bytes from one place to another. And there are applications built on top of it, like HTTP or SMTP. which is purely concerned with the business logic of things. And the architecture of IBC is pretty much the same. There's a transport layer, and there's applications like token transfers built on top, which is what we'll talk about in a few slides. But yeah, in general today, this is what the interchain looks like. It's the largest network in terms of like chains connected over one interoperability protocol. There's more than 100 chains that are connected over IBC. In any given month, IBC is processing like $1 billion worth of volume. There's nearly 2 million monthly active users. And I know this is like not the best metric, but it's sort of like a proxy for the usage. And IBC is like one of the fastest transport layers that we have today. And like the average latency to send a packet is about 22 seconds, which is like a far cry compared to some of the other solutions out there. Yeah, and so like what IBC is sort of aiming to do, how can I pull out a laser? Oh yeah, okay. So IBC is sort of trying to, the vision is to standardize at the transport layer. So today we have all these different protocols like Axela or Layer 0, and every single bridge has its own transport layer. And that's why tokens sent over Axela are not fungible with tokens sent over Layer 0 are not fungible with tokens sent over IBC. But like an industry goal should be to eventually standardize upon one transport layer so that like from a developer standpoint, you can just write your applications and plug into a particular transport layer and not have to think about fungibility, how are messages sent from one place to another, how secure are those messages, etc. Yeah, and like previously we spoke about the 3 different layers: state layer, transport, application. IBC functions in the same way. So on the state layer, we have light clients, and we'll talk about what all of these terms mean in like the next slide. But for now, let's just say that like the state layer is comprised of light clients, which could be like a Comet or Tendermint light client, Grandpa light client for the Polkadot ecosystem, and so on. The transport layer consists of different abstractions like connections, channels, relays. We'll talk about what these terms mean. And the application layer has token transfers, which I'm sure like anyone who has used IBC is familiar with. Essentially just moving tokens from one chain to another. Interchain accounts is essentially cross-chain contract calls. So staying on chain A and executing a contract call on chain B. And interchain queries is essentially just reading data from chain A and chain B. Okay, so coming to like the high level architecture of how IBC works. You have chain A, you have chain B, and we'll sort of work our way up from the bottom of the stack. Yeah, so like I mentioned, IBC uses light clients. And to sort of take a step back, people might be familiar with what a full node is. A full node, is basically just a server or a computer that has the entire history of a blockchain. It is downloading every single transactions, and it is executing every single transaction. So at any given point, it knows the state of a blockchain. Unlike a full node, there are also light nodes, which are just resource-constrained environments in terms of like they just don't have the same amount of bandwidth, RAM, or storage that a full node does. And so it is not storing the entire history of a blockchain, and it's not executing transactions. Instead, what a light node is doing is that it is just connecting to a full node, requesting block headers, and verifying those block headers. Now, an IBC light client is essentially just an on-chain version of a light node. So chain A has a light client of chain B, and vice versa. Chain B has a light client of chain A. And all these, the only thing that they're doing is verifying block headers using proofs or Merkle proofs. All right, so that's basically what light clients is. Again, just to summarize, a light client is basically just a very lightweight representation of a counterparty blockchain, and it's verifying block headers. Yeah, and then going up the stack, we have connections. This is not very important. Application developers do not need to concern themselves with this. But a connection is basically just a layer that connects two different light clients on two different chains. But what's more important are channels. So this is what app developers will be working with. And channels are sort of like the conduit through which data packets are sent by applications. So like if tokens are to be sent from chain A to chain B, they'll be going through a specific channel. Yeah, and so like when chain A wants to send a message to chain B, chain A is not like beaming these messages to chain B. Like there is some entity in between that's responsible for picking up a message and ferrying it to the counterparty. And that's what a relayer does. So for instance, when chain A wants to send a message to chain B, what it's doing is that it is storing that message in its own state. And when that happens, an event is emitted, or like a message saying, hey, chain B, like I want to send a message to this particular chain. And relayers are sort of monitoring for these sort of cross-chain events. And when a relayer sees that chain A wants to send a message to chain B, it will pick up that message, construct a data packet or an IBC packet, and that packet will essentially contain, like on a very high level, the important things are the header itself, like the root of the Merkle tree. It'll contain the actual bytes that are being sent, and it'll contain a Merkle proof. And those are the only three real things that chain B needs to verify that this message is valid. Yeah, okay. So once this message arrives on chain B, it sort of goes down the stack all the way to the light client. The light client will verify the proof, the header, and the bytes. And if everything checks out, light client will be like, all good. And then that message again goes up the stack through the connection, through the channel, all the way up to the application. And then the app can perform any custom logic. So in the case of token transfers, it'll just be minting tokens. Cool. Do we take questions now, or do we take questions at the end?
If they're relevant, you can dig into them as you go, Adi. So yeah, one of the questions that has come up is what is the state layer?
Right. The state layer is exactly like it is the layer that's performing the verification. So in the case of IBC, it is light clients. In the case of something like an axilla, it would be the validator set of the blockchain itself. Any part of the stack that's actually performing message verification, or like validating the message itself. Like, is this correct? Did this come from the chain that it's, like, is this coming from the right place? Is this intended for the right place? All of those verifications. Cool. All right. So talking about like types of interoperability protocols, from like a 10,000-foot overview, you can sort of bucket them into two categories, trustless and trusted. And there is a spectrum here, and we'll get to that. So you can think of like quote unquote trustless bridges as a layer 1 to a layer 2 bridge. So, going from Optimism to ETH mainnet, like the canonical bridges. And you call them trustless because they're actually verifying how messages are executed using fraud proofs or validity proofs. I don't know if we have time to get into like how fraud proofs and validity proofs work. We can talk about that later if people have questions, but I'll just like skim over that for now. And then in the case of trusted, all these other solutions like, well, IBC technically is a trusted solution. Axilla, Wormhole, all of these things fall under this bucket, but there is a spectrum there. Like the security properties of IBC is different from the security property of other third-party solutions, and we'll get to that. And sort of breaking them down further, we can categorize them into four buckets, which is like canonical bridges, which is what the bridge going from an L1 to L2 or back. So Arbitrum bridge, Optimism, all of these things. There are locally verified protocols, which are things like across a Stargate, where like liquidity pools are used on a source and destination chains, and funds are moved through liquidity pools by like market makers or solvers or fillers, relayers, whatever you want to call them. And these protocols don't have an actual transport layer. They just piggyback off of an existing transport layer. So you can have locally verified protocols on top of IBC or on top of a canonical bridge like Arbitrum. And we see that a lot today. Natively verified, you call them natively because it is the chains themselves that are verifying the messages. So in the case of IBC, there's a chain A and a chain B, and it is those chains themselves who are verifying the messages without a third party. So this could be by using light clients or by using zero knowledge proofs. And an example is IBC or Rainbow Bridge, which is like a bridge between NEAR and Ethereum mainnet. And finally, we have externally verified protocols. These are like middleman chains, and we will talk about that in the slide. Did I see a question, or should I keep moving on?
Yeah, Serene, I think you have a question as well there if you wanna ask.
Yeah, absolutely. I think for just to help context to our audience, are there any limitations to the types of data that can be transferred using IBC, of course?
No. So you can send any message, like I said, if it can be encoded in bytes, you can send that over IBC, and we see that today. Like, for example, like of course we have token transfers, but we also have a feature called interchain accounts, which is almost like a message inside a message, and you can send any information in that. So we see people sending token transfers, but we also see people sending messages like send tokens and then swap them on the destination and then send it back, or swap it and send it to another chain. You can have like cross-chain governance over interchain accounts, or even like, I guess like you could technically have NFTs transferred over interchain accounts as well, even though we have a separate protocol for NFTs. So yeah, there is no limitation on the kind of data that can be passed over IBC.
Awesome. One more question, and I know you mentioned that you might dig into this a little bit later, so feel free to keep going if not. But I think it would be helpful to know how IBC does manage privacy when transferring across the chains.
Do you mean like can relayers see the information that's being sent?
Yeah.
Right. Like they can see the actual bytes. They can view the information, of course, but they can't change. Even if they do change the actual message that's being sent, it won't. The light client on the counterparty, like that check will just fail because the actual bytes has changed, and so it will not hash up to the proof that's being provided. So like even if they do change something, like the protocol is just going to reject it. But yes, they can see the actual information that's being sent. Yeah. Okay, cool. Yeah, so coming to like the different types of the architectures that we have in terms of bridges. So the first one, like externally verified protocols, this is where there is chain A and chain B that want to talk to each other, and they use like a third-party chain, which sort of observes cross-chain events, comes to consensus on the validity of that message by using its own validator set, and then it'll sort of write that data to chain B. And the benefit of using this approach is that it's fairly easy to integrate because it's just about deploying a bunch of smart contracts on the source and destination chain. But the drawback is that you have this weakest link problem where, for example, if the TVL on the bridge contracts, so the total value locked on the bridge contracts, A and B, if they start exceeding the value than what is staked on this bridge chain, then that becomes like an attack vector. So in that scenario, someone is, economically incentivized to sort of rack up a majority of stake on this bridge chain, compromise those contracts, and then steal user funds. So that's like one of the main issues that we see with like these third-party solutions. yeah, and like examples of these are like wormhole, axelar, and so on. Yeah, and then we have canonical bridges, which we talked about. This is between L2 and L1. So like, for example, the base, rollup, and Ethereum mainnet. And yeah, the benefit is that on paper, it is the most safest form of bridging today because they use either fault proofs or ZK proofs. And so they are actually verifying how the messages are being executed itself and not trusting any validator set or trusting a third-party chain. The drawback, though, is that it is only used for token transfers today. So you can't have like a cross-chain contract call. Like Base can't use its own native bridge to make like a contract call on Ethereum mainnet. That just doesn't work. Also, it's very specific to a particular L1 and L2. So the canonical bridge between Ethereum mainnet and Base cannot be used for Arbitrum, for example. So it's specific to those chains. Coming to locally verified protocols. So these are things, it's like, I feel like it's sort of all the rage today. These are the things that use like market makers or solvers or fillers or like intent-centric. And these protocols don't actually, there is no actual message being moved anywhere. There is no real transport layer. Like I said, they exist on top of an existing transport layer, like a canonical bridge, for example. And what happens here is that, let's say a user on Base, they want to send 10 USDC to their account on Ethereum mainnet. The funds, initially, they'll be sent to the market maker or the solver's account. And so if people are familiar with how L2 to L1 bridging works in the case of optimistic rollups, there is that 7-day fault window. So, a user can only get their funds after 7 days, which is sort of not acceptable in terms of UX. So one of the benefits of using this solution is that you can bypass that 7-day window and get your funds immediately. And so these protocols can do that because they run a full node, or in the case of Base, they'll run a sequencer, and they can immediately verify that this transfer did indeed happen, and that it's also that transaction has also been submitted on Ethereum mainnet. So what the protocol can do is that once this has been proven, the same solver can unlock funds from their account on Ethereum mainnet to the user's account on Ethereum mainnet. So if they get 10 ETH here, they'll unlock, let's say, 9 ETH and just take 1 ETH as the fee. Yeah, so like the main benefit is that transfers are cheaper, faster. You can bypass the 7-day challenge period or the fault period. But one of the drawbacks is that you're limited in terms of what you can do. So like contract calls are much harder over locally verified protocols. Some protocols don't even have cross-chain contract calls. So yeah, in terms of expressivity, like application developers are limited here. Yeah, and finally, we have the bucket that IBC sort of falls under, which is natively verified protocols. This is where you use something like a light client to verify the messages. And yeah, you're not like trusting a third-party solution like another chain itself. And the benefit is that it's one of the it's like gold standard for security today. But the drawback being that it's much harder to deploy these kinds of solutions on new ecosystems or like new VMs and so on. But yeah, like that's something that we are working on right now. We're working on something called IBC Eureka, which will be like a V2 of the protocol. And that sort of seeks to solve this issue of making it, to make it like easier to put on different like VMs, chains, ecosystems, etc. So yeah, stay tuned for that. Yes, so like finally coming to like a comparison of everything versus IBC. So like IBC in the case of externally verified protocols, I mentioned like in the case of IBC, you just trust the chains A and B that's involved. In the case of externally verified, you trust chains A and B, but also this third-party chain C. And sometimes that third-party chain C can be the weakest link. So it doesn't matter how economically secure A and B are. if C is the weakest link, then that whole system can be compromised. Both solutions support arbitrary message passing, so like send any sort of message. And so also one of the main benefits that IBC offers is that it has these things like packet receipts or acknowledgements or timeouts. And like acknowledgements, for example, it is just something that says, so when chain A sends chain B a message, first that message will be sent to chain B, and then chain B sends back an acknowledgement to chain A saying that, this message was received successfully and processed successfully, or it'll say that something wrong happened. And this is useful for one, users, because you get a confirmation if your transaction was successful or not. And two, for developers, you can use acknowledgements to build composable actions. For example, let's say you want to send a transfer and then swap those tokens. You can only perform the swap action if you know that the first action was successful. And so you can use the acknowledgement as sort of like, an indication that, okay, the transfer happened successfully. Now I can send a second message to swap those tokens. So in that case, like that's something that's useful, and it's very unique to IBC, and no other interoperability protocol today has it. In the case of like externally verified, you're sort of sending a message and hoping that it is successful there, or as a user, you have to sort of change your interface or change your wallet to see, okay, did I get my funds on the destination chain? Yeah, in terms of costs, IBC does not charge anything. There is no in-protocol rent extraction. Externally verified solutions have like additional fees on top of the transaction fees. And IBC is it's not controlled by any single company. We have no profit motive. But that's usually not the case with like externally verified protocols. It's sometimes, backed by VCs, it's a company, and they're driven by like a profit motive. IBC versus canonical bridges. Yeah, IBC uses light clients. Canonical bridges, they use fraud proofs or validity proofs. Canonical bridges, they don't support arbitrary message passing. Like I mentioned, they are only used for token transfers today. And they don't have like acknowledgements or timeouts, etc. Similar to IBC, canonical bridges also don't charge an additional cost of rent extraction. And in terms of like the organizational structure, it can really just vary depending on which protocol we're talking about. And yeah, finally coming to locally verified solutions, IBC uses light clients. The like locally verified solutions, they use market makers who are running full nodes. Yeah, they're limited in terms of what you can do. You can only transfer tokens today, and like contract calls are very limited. They charge an additional fees, like a swap fee or a router fee, which is not the case with IBC. And these solutions are also usually controlled by like a company backed by VCs and so on. Yeah, so I think this is the last slide, like just going through the different solutions and the main properties. In the case of like IBC or like canonical bridges, like I mentioned, they're verifying execution. Native solutions, they're verifying using light clients. Externally verified protocols, they're using like a third-party blockchain. And locally verified solutions, they're sort of tapping into an existing transport protocol. The trust assumptions for different protocols are, in the case of canonical bridges, for optimistic rollups, the assumption is that there is at least one honest full node in the network. So this means that there is, somebody in the world running a full node, and they're watching if the system is correct. That is like the trust assumption there. In the case of ZK rollups, the assumption is that the ZK circuit itself is implemented correctly. In the case of IBC or like native protocols, the trust assumption is that at least 2/3 of the validator set is honest, and this is the case for like Cosmos chains, or like chains that are using Comet or as Tendermint. For externally verified, again, the trust assumption is that chains A and B are secure, but also this third-party chain also has an honest majority of validators. And for locally verified, the trust assumptions boil down to the trust assumptions of the underlying transport layer. And the main trade-offs here is that for canonical bridges, it's specific to an L1 to L2. For native bridges, it is sort of harder to implement or extend to other ecosystems. For external protocols, the trade-off is that you're trusting this third-party chain. And for locally verified, it's limited to token transfers or like fungible actions. Yeah, so that's pretty much everything. Thank you for listening. Yeah, we can talk about like any questions that people have.
Yeah, lovely stuff, Adi. Thanks for that. There's more of a comment in the YouTube section here that sort of relates IBC to sort of TCP/IP, while looking at the other protocols, particularly from that send and pray aspect. I would expect that they sort of more closely mirror that of UDP. Would you agree with that?
Yeah, I think so. Like in the case of TCP as well, you have this message that's being sent and you have an ACK that's sent back. And I think like the original design of IBC, or when people made the initial specification for IBC, they were pretty like motivated by the design of TCP/IP. And you can even read that in the spec itself. And yeah, that's something unique to IBC and other protocols don't have, which I think is also the case with UDP. Like you sort of send your message and hope that it gets there. Yeah.
Yeah, absolutely. So on that ACK front, I'm also wondering about like timeouts of packets and what happens if you're in a token transfer and it doesn't reach the destination chain.
Right. So when chain A sends a message to chain B, in the payload, it is specifying that this message should be processed within this time. So if the message is saying that, hey, this packet should be processed by 3 p.m., but let's say it's 4 p.m. and that message has still not arrived, then the timeout message, so like chain B will sort of emit a timeout event, and a relayer can sort of construct a timeout message, send it back to chain A. And what that happens is that from a user perspective, so when you're transferring tokens, you're locking your funds, right? And when a timeout is received on chain A, you can sort of revert state. In the case of user, those tokens are like just unlocked back to the user itself, so that they're not like losing funds or something, for example.
Great. Yeah. So funds are safe, and that state sort of reverts. What if, because you mentioned about chain B, sort of providing that information. What if the relayer is down, for example?
So in any given between two chains, or for any given channel, there can be multiple relays. So relays are permissionless, meaning that anyone anywhere in the world can run a relayer, and that means you're running a full node of chains A and B. So even if one relayer goes down, that anyone else can really just run a relayer, pick up that message, and send it anyway. And we see that between channels, like any given channel has multiple relayers active, so it's never like just one relayer per channel.
Things are sounding pretty resilient. We have a question from the audience as well. Can we talk a bit about how different chains integrate IBC? So the different integration options.
Right. So if you're using the Cosmos SDK today, you get IBC out of the box. So it's IBC Go, which is the Go implementation of IBC. And it's already like within the Cosmos SDK, and you can use it. There's like no integration efforts needed. But if you're using some other VM or like a rollup framework, etc., then integration is mainly three things. So one, you need a light client implementation. You need the transport layer implementation. So this is things like channels, connections, etc. And you need a relayer specific to your VM that can read events, construct messages, and like send messages back and forth. So those are like the main three categories, or like the main three things you need in terms of integration. But again, this is all of this information will kind of be outdated very soon, because like we're working on like the V2, which is IBC Eureka, and that makes things considerably easier. And the time to market for a completely new chain using IBC will be like 10x going down. So yeah.
Exciting stuff. We're looking forward to the Eureka side there. Bringing this back to the Ideathon, can you think of some implementations or some translations from the things you've been speaking about that might be helpful for people using the Idea Builder during the Ideathon?
Yeah, for sure. So I think one of the things is that, so we talked about like different applications, token transfers, interchain accounts, etc. Those are the apps that exist today. But if you feel like for the Ideathon, you don't need to be limited by those applications. If you think there's a particular application that doesn't exist on IBC today, and you would like to present that, you don't need to have the implementations down to a T. If you just want to talk about it on a high level, feel free to include that in your Ideathon, mention it, like that's awesome. And similarly, like one thing that I'm personally interested in right now are just like these market maker approaches. So, and I believe that is also a track in the Ideathon under intents and incentives. So these are things like, you could in theory have the IBC transport layer, but have a market maker on top of it, like a solver network. So a benefit of this would be, having IBC between Base and Ethereum, where users are sending funds from Base to Ethereum, and IBC takes 7 days to settle, but you can have the solver network on top of IBC, providing instant bridging to users in a matter of like milliseconds. So that could be like a good combination of two different types of architectures that we talked about today, and it's also like a track with an Ideathon. So that's like something you could use.
Lovely stuff. We have a little bit of time left here, so I'm wondering if you want to. You mentioned a little bit earlier, dig into a little bit on some light fraud proofs, validity proofs, and maybe then comparing that on the Merkle proof and Merkle root side of IBC.
Right. Let me see which slide that was. Okay. Yeah. So yes, I mentioned like quote unquote trustless bridges. Why are they trustless? Because they're using fraud proofs or validity proofs. So what is a fraud proof? Oh my God, this is so much to explain. But anyway, we'll get there. So we have layer ones like Ethereum mainnet, and we have layer twos, roll-ups like Base or Optimism. And as of today, when you go from the L1 to the L2, bridging is fast. That's okay. That's fine because on the L2s, the message can be verified instantly, but that's not the case when you go the other way. When you go from Base to Ethereum mainnet, for example, it takes 7 days. Why does it take 7 days? Because the Ethereum state machine is limited in terms of what it can do, which is exactly why there are layer twos to sort of branch out execution, because the Ethereum blockchain does not want to, I mean, even though the vision is to be like this world computer, the roadmap is sort of contradicts that. So the Ethereum blockchain cannot execute all the transactions in the world. Instead, it sort of pushes those responsibilities to the layer twos. And when a layer two is saying, hey, a user on my chain wants to move funds to Ethereum mainnet, what is happening is that transaction is being submitted to something called a sequencer, which you can just think of like a very bulky computer. And the sequencer is taking that transaction and putting it on Ethereum mainnet. And when that happens, Ethereum mainnet is not executing that transaction. Ethereum does not even know if that transaction is valid. It is just accepting that transaction. So who is checking if this is correct or not, right? So in the case of optimistic protocols, you have entities called watchers, or the name differs based on what implementation, but let's just call them watchers for now. And these are people running full nodes of the layer 2 of Base, for example, and they can check to see if the information that the sequencer is saying is correct or not. If the sequencer is saying that, hey, the state of this block is X, and if me as an honest watcher, I see that the state of that same block is Y, then I can challenge that. I can challenge that statement by the sequencer using something called a fraud proof. And the fraud proof is basically just saying, the fraud proof is essentially, it's a bisection protocol. So in that block, let's say there are 1,000 transactions, that block will be split into two, 500 and 500. And, I will point out and say that the wrong transaction is in the first 500. And then we'll take just that 500, split it again into two, so 250, 250, and that goes on till we get to like the final opcode where I say that, hey, if you take this transaction, if you take this state, apply this single transaction, you get my view. And if you take the same state and apply the same transaction, you get the sequencer's view. And then the Ethereum mainnet will only execute that single transaction. So instead of having to check all those 1,000 transactions by itself, it is maintaining security in a very lightweight manner by just having to execute that single transaction, which is, very trivial. And then it can just see for itself, okay, is the final result X or Y? Like, who is correct? Am I correct, or is the sequencer correct? And if the sequencer was wrong, the sequencer is slashed. If I'm wrong, I am slashed. So that's what a fraud proof is. And this is exactly why layer 1 to layer 2 bridges are secure, because, they are secure assuming that an honest watcher exists in the system. Okay, and coming to ZK rollups, so in the case of ZK rollups, going from a layer 2 to a layer 1 does not take 7 days, because the messages that are being submitted also has like a ZK proof or a validity proof. And that's just like a ZK proof saying that, hey, all these transactions happened, this is the final state, and here's a ZK proof to verify that. And Ethereum mainnet, again, can like very trivially verify that. It still might take latency on the order of like a few hours. It's still not instant transactions. But that is also like a fairly trust minimized manner of verifying transaction execution. Yeah, so that's why I said it's trustless. Was there a second part to the question?
Yeah, I mean, if you want to tackle like how IBC differs from that side, and then I also want to ask you what excites you about IBC compared with the other protocol implementations we've spoken about today.
Right. So in the case of how messages are verified on IBC, it's obviously different from validity proof systems because we don't use ZK proofs, even though you could have a client that's verifying ZK proofs. You could say that it's kind of similar to how fraud proofs are verified, because again, you're taking a message, you're taking a proof, and you're seeing if it's correct or not. And that's exactly what IBC is doing. You're taking a block header, you're taking, you can think of the block header as like the root of the Merkle tree. So yeah, like the root of the Merkle tree. The actual information that's being sent, the bytes, which is like the leaf of the tree, and you have a proof that shows, given this leaf, you can sort of work your way up to the root and make sure that everything hashes up and it's all correct. So yeah. And coming to like what excites me about IBC compared to other protocols, well, I think IBC has always sort of put emphasis on security. Like it's been live for more than 3 years, and like no like security vulnerabilities. And I think I also mentioned like initially it's still like one of the fastest protocols out there today. So that's also something pretty cool. It's also the largest network, which is also great, like 100 plus chains connected over IBC. And today we also see not just Cosmos, but also other ecosystems being connected, like Polkadot/Kasuma, for example, or Solana. Like there is a Solana connection to IBC, which is built by the composable team. So IBC is being extended to other ecosystems, which is exciting. And I think the thing that I'm most excited about right now is IBC Eureka, and I think it'll sort of change the whole landscape of how people perceive IBC today, especially for different VMs and in terms of integrating into like an SVM or the EVM, for example. So that's something that I'm particularly excited about, which for me is like it's like the best of both worlds, where you still have the core properties of IBC with its security and its applications, but you make it significantly easier to sort of, implement/extend onto other ecosystems. Yeah.
So exciting things in the works. Yeah, no, that's lovely. So I'm not seeing too many additional questions, but yeah, I'm looking at the chat here. So yeah, I think that covers all of my questions. If any of us also have additional questions, otherwise, yes, Serene.
Yeah, you briefly touched up on it, but could you go into a little bit more detail about IBC Eureka and what everyone could get excited about in the hopefully near future?
I don't know if I'm going to get trouble by like marketing people for talking about it. Yeah, but that's fine. So what can I talk about IBC Eureka? So like I mentioned, it's something that like the IBC community has been thinking about in terms of, what is IBC at its core? At its core, it is just a way to transfer messages with like-client backed security. So it's a way for applications on different chains to talk to each other using like clients. Like that's the real core essence of IBC. And so how can we maintain that while solving some of the main issues that people are facing? And one of the main problems by users is that it's hard to put IBC on EVM, for example, or it's hard to put IBC on like other VMs. And the main issue for that is because IBC has a number of abstractions that we talked about, like connections. And there's something that there are handshake protocols that go into establishing a connection, which is like a 4-step protocol. There's a handshake that goes into establishing a channel, which is also a 4-step protocol. So it's almost like you have all of these messages that initially need to be performed even before a user can send a first transaction, and that's a lot of overhead. It's fine for Cosmos SDK chains today, but other VMs were not built thinking about IBC in mind. And so, for example, in the case of EVM, that takes up a lot of gas. It's costly. It's also building a relayer specific to a VM is something that takes time. So the main goal with IBC is to sort of strip away all of the things, like understanding what is the core of IBC and then sort of chipping away at the rest to still maintain like the main benefits of IBC. So things like removing handshakes, supporting different encoding structures. Like why should we be limited to protobuf? Like removing those kinds of things. Yeah, and like yeah, and essentially just making it easy to have like an osmosis talk to Ethereum mainnet or like rollups, and potentially other VMs as well. So yeah, that's what we're working on with IBC Eureka.
Further expanding of the internet of blockchains. I love it. Excited for it. And yeah, so bringing this all back again to the Interchain Ideathon, we are really excited to see what you go and build. Some of the awesome stuff that Adi's covered here is going to be really helpful in terms of getting stuck in with the Ideathon that's happening at the moment. Yeah, so you can, if you haven't headed to it already, it's ideahackers.ibcprotocol.dev. is where you're going to find all of the exciting information about the Ideathon, which is running from 2 days ago when we kicked things off. There's a few other videos that might be worth watching that also introduce some of the event and the Ideathon itself. And it's going to be running through October 27th. So yeah, we've already started to see some submissions coming in, so keep them coming. And yeah, thanks for being a part of it, and a special thank you to Adi for this awesome presentation and answering my long list of questions. It's been a super fun one, and yeah, looking forward to see what all of you build and engaging with us in Discord. So there is a dedicated channel in Discord for the idea hackers. We also, separate to that, we have a neat Interchain GPT. It's a chatbot inside of the dev support channel that you can also ask IBC questions to, and it'll answer based off of the documentation. Otherwise, we're happy to help chime in there as well. So yeah, if you need additional support, you can find us over there as you go through your journey of building your ideas and mapping them out in the really cool tool that we have on that side. Other than that, looking forward to seeing some of you at Cosmoverse towards the end of the month. And for those of you who are hacking as part of the Ideathon, the best of luck. And there's some really sweet prizes up for grabs, as well as that trip to see if we can turn your idea into reality. But yeah, huge thank you to Adi, huge thank you to Serene, huge thank you to all of you who tuned in, and Oscar, our guy on the tech side here. And we will catch you soon and on Discord. Thanks all.